So finally, let me give you a brief idea of some of the non-ideal effects that you might actually encounter in real life. One of them I already mentioned is dispersion. And so, as I mentioned before, dispersion is the effect that essentially will lead to different frequencies traveling at with different velocities, which you will see in real life as pulse broadening. Now, where this is coming from, if you go back and you look at the equivalent circuit of a microstrip or any other transmission line that we discussed, it basically has these four main elements. It has the resistance per unit length, inductance per unit length, capacitance per unit length, and conductance per unit length. And unfortunately, none of them is constant. For example, if I look at the resistance per unit length, it will actually increase as a function of frequency, so things become worse and worse. One of the main reasons is actually the skin effect, right? So for DC, as we'll see in a minute, the current actually occupies the entire volume of the metal that you give it. But as the frequency is increasing, the current actually tends to only occupy the edges of the microstrip line. So the current will only flow on these edges of the microstrip line and not inside the volume. And that will naturally lead to an increase in resistance. Usually that increases as a function of the square root of frequency. Similarly, if I jump to G to talk about the other effect of loss, the dielectric loss also increases as a function of frequency. And that is true for any dielectric. That's related to the material issues. You can imagine, for example, that when you polarize a dielectric with an electric field, and you shift that electric field as a function of frequency, you make these dipoles actually reverse polarity. But when that happens, there is friction and there is loss. Hence, by the way, microwave cooking works. Right. Similarly, inductance will change as a function of frequency. Not so much, but it will. Again, it's, for example, if you remember from your undergraduate days, if I consider a coaxial line, for DC, I have actually current that flows inside the volume, which means I have an inductance in the volume. Now I don't. And so that means the inductance will actually become lower. Similarly, the capacitance per unit length has a weak dependence because the dielectric of the medium, epsilon r, also changes with frequency as well. So lots of things can go wrong as you imagine shifting things over frequency. And that's, by the way, one of the reasons why wideband circuits are actually harder than narrowband circuits. This is an image that I actually took from the book. I don't want to go actually in this class into too many electromagnetic details, but what I do want to show you is actually this top picture here mostly, which it's a good mental image to have. This picture shows you the current and charge distribution at DC. And as you can imagine, this is also approximately true for low frequencies, megahertz type of thing, where mostly you have a uniformly distributed current and uniformly distributed charge in the microstrip line as well as in its ground. But as the frequency keeps increasing, that geometry will actually break. And you will see, for example, for high frequencies, which is the focus of this course, most of the charge and current will be at the edges, and most of the current and charge for the ground plane will be at the edge of the ground directly underneath the microstrip line. So keep that in mind, because a lot of things we forget that, and we basically fail to realize why loss, for example, increases as a function of frequency. And by the way, keep in mind, as I mentioned before, that loss is a cause of dispersion too. So you may have taken the best possible dielectric here, epsilon r, with a loss tangent of maybe 10 to the negative 4, and still find out that the dispersion is not good enough because of the metallic, the ohmic loss. This is an example of an actual simulation, and you will see essentially a microstrip line with two different impedances. So here's the impedance of 50 ohms, here's the impedance of 25 ohms, and we are basically plotting here the effective dielectric constant of this effective medium as a function of frequency. Notice that the frequency actually changes here by multiple octaves. It goes practically from DC all the way to 18 gigahertz. But what is interesting to see here is that, first of all, the dielectric constant change, the effective dielectric constant change, is not negligible. It will basically, let's say you were designing a circuit from 1 gigahertz to maybe 10. So if you look at from 1 to 10, the dielectric constant, let's say for the 25 ohm case, it will change roughly from 7.3 or so all the way to almost 8. And again, that's a pretty severe change. For 50 ohms, it's a little bit better. And I'm not going to answer it here, but go ahead and think of why 25 ohms is worse. And the answer to that lies to the physical geometry. So remind yourself if a line that is 25 ohms is narrower or wider than a 50 ohm, and the answer will immediately pop up. So that is an interesting thing for microstrip line that you should keep in mind. Similar things happen for coplanar waveguides. So this is another example of the effective dielectric constant for a coplanar waveguide for a large geometry as well as a small geometry. But what I do want you to notice here is that in general, the dispersion, as I discussed before, is smaller in a coplanar waveguide line compared to microstrip. And so yes, you do suffer dispersion in CPW, but it's a lot less than microstrip. And also I want you to see that both for small and large geometries, the numbers are comparable. And so that knowing roughly these numbers, you don't have to memorize them, but at least having seen them will give you a good idea of what kind of epsilon change are we expecting here. Will it double, or will it be 10% different, 20% difference? That's the point of these graphs. I'd just like you to have a physical intuition of how much things do change. This is an interesting image I also took from our book in terms of addressing some of the multimode effects that you might see in a coplanar waveguide. So as I mentioned before, one approach that we sometimes do is we will periodically, every so often, we will load this with microstrip straps, with straps that equalize ground planes. This is also a pretty common geometry when we make a T-junction. So this is a T-junction for a CPW line. And again, we're really scared of imbalancing the ground planes here. So those straps will take that into account.